Alright, so let's pick up where we left off on Tuesday here in Chapter 7. We were talking about individual bond polarity, and we said when two atoms are sharing electrons, that electron density, like any electron density, is fluid and it can shift around, and it should be pulled more toward the atom that's more electronegative. That creates a polar bond. If that entire molecule is just two atoms sharing electrons, then it also makes a polar molecule. And so that molecule then can line up next to other molecules that experience intermolecular attractions, which we talked about. That's really what we're trying to get to here today. So there are really two factors that are required for an overall molecule to be polar. So for a molecule to be polar, one factor is has to at least have a covalent bond somewhere that involves atoms with different electronegativity. Right? So, for example, a carbon and an oxygen have a different electronegativity. So CO2 fits one of the requirements for it to be a polar molecule or to have a dipole. The other requirement, though, is it has to have some degree of asymmetry. It can't be a completely symmetrical molecule. Because to have a polar molecule, which means it has a dipole, it has to have opposite charges on opposite ends. That means one end of the molecule has to be different from the other end. It has to be asymmetrical. It can't be symmetrical on both sides. So that's a problem for the CO2 because the CO2 ends up being nonpolar. So there's really two types of analyses that I'm going to show you, and you can choose the one you like. But for CO2, you've got to have the Lewis structure drawn correctly. You've got to analyze the geometry on the central atom. In this case, there are only two electron groups, no lone pairs, so it's linear. Once you draw the molecule with the correct shape, then you can begin to analyze the polarity. So to do that, one way, which I think most people generally prefer, is to see the electron shift. Use little arrows to show the direction of the shifting for the individual bonds. Then draw in the areas of partial positive and partial negative, if there are any. Right? So the oxygen's more electronegative. The fluid electrons between the carbon and the oxygen move a little bit more toward the oxygen, and that's true on both sides. As the electrons move away from the carbon, it will leave a bit of an electron deficiency there, and the carbon will take on a partial positive. So once you show the partial charges on all the atoms, though, the next step is to see, is there an overall average position of positive that is on one side of the molecule and an average position of negative that is on the other side of the molecule. A dipole, or a polar molecule, has to have two opposite ends with opposite charges. So we're trying to find where are the centers of opposite charge. Are they on opposite ends or not? So in this case, the average position of positive, obviously in the middle. The average position of negative is also in the middle because I have one negative on the right, one negative on the left. On average, or the central position of negative is going to be right between them. So I find the center of negative and the center of positive, or the average or central positions of negative and positive. If they're in the same location, then I know that it's nonpolar. And it does not have a dipole, and so it cannot experience dipole-dipole attraction. It can only experience London forces. The other way is to use a vector method. So using a vector method, I just create a coordinate system here. And in this method, I would use arrows to show the electrons moving. Right, so I realize there's an electronegativity difference between the carbon and the oxygen. The oxygen's more electronegative, it's pulling electrons. I use an arrow to show the direction the electrons are shifting in. And I would use a longer arrow the greater the electronegativity difference would be between those atoms. Because the electrons would be shifting more heavily or more prominently to that side. So once I have my molecule written on paper in its correct three-dimensional shape, which in this case we discovered is linear, and I have arrows to show all the individual bonds, then I create vectors for my arrows and plot them from the origin. So I would take one arrow We'll call this arrow 1. I would draw it starting at the origin. And then subsequent arrows begin where the last arrow ended in a vector method. So arrow 2 would be starting at the end of arrow 1, and it would actually be the same length but in the opposite direction. So that gets me back to the origin. And so if I discover that my vectors, when added together, go right back to the origin, that means there's no net vector or no net overall polarity. So I get the same answer using the vector method or the other method. Both methods suggest that don't have a dipole. There's no one net overall arrow showing the direction of polarity because my arrows individually are canceling out. Any questions about that? Yes? This is supposed to be a 1. Sorry. Other questions? All right, let's look at another example then. So here I've got water. So I can look at both methods. Got my Lewis structure for water. It's important to write it like that and not like this. Initially, if you write your Lewis structure like this, that's okay, but then in this process you have to think about the geometry around that central atom. Since there are 4 total electron groups, the angles are going to be around 109. It's going to be a tetrahedral electron group geometry. So that means when I think about where the atoms are, I can't put them in a straight line. The angles are not 180. The angles are 109. I have to write the molecule. For really, either of these methods requires me to write the molecule with the correct geometry and to show it as best I can on paper with its correct 3-dimensional geometry. So once I realize that it's bent, I would draw it bent. And then I would look at the individual bonds shifting. They're always going to shift toward whatever atom's more electronegative. That's going to create a partial negative there and some partial positive on the other atoms the electrons are shifting away from. So then I find my central area of negative. Well, there's only one area of negative, so I know where that central area of negative is. And I find my central area of positive. If I only have 2 positives, the central area of positive is going to be right between them. And so each hydrogen carries some positives, so the central position of positive will be between them. Then I use an arrow to connect the positive to the negative, and that is the direction of polarity for the molecule. If I use the vector method, I'd do the same thing. So I'd see each individual bond as a polar bond, 1 arrow to represent each individual bond. Then I would tick either one of those arrows, start with that one, start at the origin, move out, draw that first arrow, then start the second arrow where the first arrow ended, and add that to the first one, and I find the same overall net arrow here that I got here.
So the arrows are following the line of which way it's going with the X and Y.
Yes. So that tells me that it's polar. Not only does it tell me it's a polar molecule and that it has a dipole, these methods also allow me to determine the direction of the dipole, which is really important when I'm thinking about intermolecular attractions, because I want to know in water that the direction of the dipole is from the hydrogens pointing toward the oxygen. That means the hydrogens are on the positive end, the oxygen is on the negative end, and when that molecule is moving around in space next to other molecules, it's going to line up the oxygen next to something that's positive. It's going to line up the hydrogens next to something that's negative to form some intermolecular attractions using those partial charges to make those attractions. A couple other examples. Here I have BF3. The boron is trigonal planar because it only has 3 electron domains, and they're all bonds. No lone pairs. Once I draw the Lewis structure out, then I realize the fluorine is more electronegative than boron. So each fluorine will have a little partial negative, actually a lot of partial negative because it's a very polar bond. The boron will have a lot of partial positive. However, what we said was for it to be polar, it has to have polar bonds and be asymmetrical. And this molecule is perfectly symmetrical. And I can recognize that when I realize that the center of positive is on the boron But the central or average position of negative is also on the boron, because I've got these three negatives spread out evenly from that. And if I looked at the average position of that negative, or the area in between all of the negatives, the area that's central to all of those negatives, it would also be right in the middle. And so when the area of partial positive and the area of partial negative are smack on top of each other, I know it's nonpolar. Using the vector method, I would start with vector 1, add to that vector 2, add to that vector 3, and I get back to the origin, so that means it's nonpolar. Right, a vector for each bond polarity. You don't have to use both methods, but it couldn't hurt, because then you have more confidence when both methods give you the same answer. Here's another example. This one's tricky because of the phosphorus having an expanded octet. So actually, let's skip that one. It's a little different from the ones that you would probably be seeing on the exam. This one's a good one. So I've got CH2O. This is formaldehyde. And so I have my individual bond polarities. They allow me to predict that the oxygen is going to pull electrons away from the carbon and become negative. That's going to make the carbon positive. Then I think about the CH bonds. Even though the electronegativity difference between carbon and hydrogen is not very large of a difference, 2.1 versus 2.5, it's only a 0.4 difference. It's still significant. I don't want to ignore it. And so the carbon is pulling electrons from the hydrogen. That's going to create some partial positives on the hydrogen. So should the carbon be positive or negative? Because this bond here is pulling electrons away, making it positive, but these bonds are pushing electrons toward it, which would normally make it negative. So which should it be? Is that carbon a site of overall partial positive or negative, or should it be balanced? It should be positive. And the reason is because the electronegativity difference between carbon and oxygen is much bigger than between carbon and hydrogen. Oxygen is 3.5, it's the second most electronegative element. So the difference there is 1, the difference here is only 0.4. So if there's an area of higher electronegativity difference, that's going to cause larger quantities of partial charge. So if I'm thinking about the actual amounts of partial charge, there's going to be a lot of negative there, a lot of positive here, and a little bit of positive at these sites. And that's based on the magnitude of the electronegativity differences causing a greater degree of shifting and larger quantities of partial charge. So then I can clearly see all of the negative is at the top, and the center of position of positive is mostly on the carbon, but a little bit below that, because on average I've got 3 areas of positive, and so my central area of overall positive is going to be between those 3 areas. So I would have one overall arrow then that goes from the center of positive to the center of negative. If I used the vector method, I would find the same thing. Start at the origin. I've got 3 arrows. 1, 2, 3. Maybe I start with arrow 1. Arrow 1 should be longer than arrows 2 and 3 because it represents a bond with a greater electronegativity difference. So then 2 would be here and 3 would be here. Overall, I get the same net polarity in the same direction. And so the polarity is not just about how much partial charge there is, it's also directional. That's why the vector method is useful, because vectors involve direction and magnitude. So when I see the direction of this pointing up, that's relevant to the molecule, because now I know if this molecule is mixed with other molecules, I know where the negative end is, I know where the positive end is. It's like a little magnet. It's going to be moving around and lining up those charges in a way to form attractions if it's near anything else that it can form attractions with. So when you do the lab, what I want you to do is to take a blank piece of paper and just draw an arrow on the piece of paper that looks like this. Then when you make your models, again, you can put them on that paper so I can see the arrow behind the structure, and the arrow will represent whichever side of the structure is negative and the other side would be positive. You can take a picture of that, then you can use that to represent the polarities. If you don't want to do that, you can just using a computer program, you know, you can just draw an arrow on top of the molecule on the picture. That's fine too. But when you report, your pictures of the models of the molecules you're making have to have an arrow on them if they're polar. If they're non-polar, they shouldn't have an arrow on them because they don't have opposite charges on opposite ends. I'll take a couple minutes to look at some of these examples in this simulation. It's nice to see things three-dimensionally. So in a relatively straightforward situation where I've got only two atoms, simulation is nice because I can also apply an electrical field here. Right? So if atom B is more electronegative than atom A, the electron is going to shift toward B. Right? So this arrow represents the overall polarity. Sometimes they use this area around the atom with red and blue to represent the opposite charges. That would show like where the majority of the electron density is. And so if I were to grab this and move it around like this, when I release it, what's going to happen? It'll go back to the point where the negative side of the molecule is attracted to the positive plate. Why is that side of the molecule negative? Because B is a more electronegative atom than A. If I change that and I make A the more electronegative atom, and the polarity changes, then the molecule will naturally rotate so that its negative end is lined up with the positive end of the charged plate. If I've got a molecule with three atoms, a little bit more complicated, the yellow arrow here represents the overall molecular dipole. The black arrows represent the individual bond polarity. Okay? The important distinction. The black arrows here are just showing when I have an individual bond, what direction the electrons will shift. The yellow arrow is showing that overall the polarity is from the bottom to the top. So if I were to put my electrical field on here, the molecule is going to line up like that. Because the molecule overall has a negative end and a positive end, and the negative end is going to be attracted to this positively charged plate. I can mess with the electronegativities if I want. I can make C more electronegative. If I make C the same electronegativity as A, that changes the overall polarity. I'm sorry, I made C the same as B. So if C and B are the same, this bond becomes nonpolar. The only bond that's polar is the AB bond. And so the overall polarity is going to be affected by that, and that's going to cause the molecule's overall net dipole arrow to change direction. If I make C even more polar, again, you see the overall arrow is changing. So now this is my primary area of negative, and this is my primary area of positive, so overall the arrow is going from positive to negative, from left to right. If I were to look at the vector method for that, I've got this one individual arrow, then I've got this other one in black. So the net dipole is straight from left to right, which is what the yellow arrow represents. And that determines the orientation of the molecule in space if it's going to line up next to other charged particles and form attractions with them. So if we look at some real molecules, just to give you a couple more quick examples. Nice to see the map of where the electrons are. You can see those fluid electrons have shifted almost exclusively to the fluorine. We have the overall bond polarity there pointing toward the fluorine. So that's a pretty straightforward one. Let's look at chloroform. Let's get rid of this map for a second. So the chloroform is a tetrahedral structure. Right? So the hydrogen, there's one hydrogen and three chlorines on that central carbon. So if the geometry is tetrahedral, it's a little bit tricky to show on paper. How do I show the polarity? On paper, I would want to draw this in a way that allows me to see that arrow. I wouldn't want to draw it like this. Right? On paper, that would be silly. If I take the molecule and rotate it so the hydrogen is pointing away from me, if the area of positive is behind the paper and the area of negative is in front of the paper, then the arrow is coming straight out of the paper. How do I draw that on a piece of paper? I can't, right? So if you have a polar molecule, do yourself a favor and draw the molecule three-dimensionally in a way where you can see the positive and negative ends. So I might draw it like that. You know, when I'm drawing the Lewis structure of this, I might have the carbon here, and I might show the chlorines, you know, doing something like this. Then I can see, since the chlorines are all more electronegative, and the carbon slightly more electronegative than hydrogen, overall this yellow arrow showing me that the direction of polarity is from the hydrogen down through to the area of the molecule that's right between the chlorines. And the map shows me that as well. I can see that the area between the chlorines is where I have a little bit of red color, and the area on the hydrogen is where the positive charge is located. Yeah, that's tricky with the vector method because you'd have three-dimensional vectors. So that would be more difficult. So in that case, I would probably recommend the other method of recognizing what all the partial charges are on all the atoms, and then saying, okay, well, the center area of negative, three-dimensionally, these fluorines are not all going to be in the same plane. They're going to form like a pyramid. The center of that pyramid at the bottom is where the average negative position is, and the average positive is going to be on the other side. So that gives me the arrow in that direction. So that's why it's helpful to make a model, because the model is something that actually is three-dimensional. It's easier to see. CH2F2, that's one of the, some of you guys have been working on this one for the lab, I believe. You take a look at that one. Read this for a minute. Looking at the molecule. So here's one where it's important how you draw it on paper, because if I draw the carbon and then I put the hydrogens like this, that makes the molecule look symmetrical. If I think of the molecule looking like that, being flat, I will incorrectly identify it as nonpolar, because I would say, well, these fluorines are pulling away, the carbon's pulling in, so the areas of positive and the areas of negative all average out to be in the center. If the fluorines were on opposite sides, their average position of negative would be in the center, and the average position of positive would be in the center, and that would be nonpolar. But it's not flat, it's tetrahedral. And when I have a tetrahedral, I have 109-degree angles, and if I rotate the structure, I can see that those four positions are all symmetrically equivalent, but if I put the fluorines in any two of those four positions, they're never going to be at an angle of 180 on opposite sides of the carbon. They're always going to be creating a situation that makes the molecule polar. So when I think about the true geometry, if I would draw that on paper, I would show it so the fluorines look like they're at a 109-degree angle. Then one hydrogen would be pointing back. You can see that one's labeled H1, and the other is kind of pointing out at me. That'll be like H2. So the center of positive is between the hydrogens, a little on the carbon, and the center of negative is on the fluorine. So now I can see that I have an overall arrow that indicates that molecule is actually pretty polar rather than nonpolar. And so it's important that you understand the geometries and what those actually look like in three dimensions, so when you're drawing them on paper you can give a reasonable representation of the actual shape, and then that allows you to correctly identify whether it's polar and how polar it is. Any questions about that? Okay, one more example here. This is an interesting example that shows isomers. So in this case, if I gave you the formula C2, Cl2, H2, there's really three different ways you can draw that. So this slide just analyzes two of them. But with the atoms, if I connect them in different spatial arrangements, I can get different options. So if I had the chlorines positioned on the carbons like this on opposite sides, if I were to employ the vector method or look at the areas, center areas of partial positive and partial negative, the average position of partial negative is right between where the chlorines are, and the average position of partial positive is right between where the hydrogens and carbons are. It's all in the same position. So that tells me that this one is nonpolar. If I were to employ the vector method, I would see the same thing. I would look at these individual bond polarities, and I would add one arrow to the next arrow. And I would get right back to the origin. And so this is the arrows I applied to do that. 1, 2, 3, and 4. That molecule is nonpolar. It doesn't have a dipole. If I put the chlorines, though, on the same side of the double bond, in this case, because the double bond can't rotate, if I put them on opposite sides, there's no way for that molecule to rotate back into the other molecule. And if they're not equal by rotating, that means they're different structures, and they have different polarities and different properties and different identities. So in this case, I can clearly see all the negative is on one side, all the positive is on the other side, so the average position of positive to the average position of negative gives me an arrow straight down. And if I had the same vectors, I get that same situation. Adding the vectors gives me a straight down arrow, just like I get from the other method. So that one is polar. So if I gave you this formula on the exam, then your determination of whether it's polar or not would depend on which of those structures you happen to draw. Questions about that? Why it's nonpolar? Yeah, so we're looking at the individual bond polarities by one method. So this arrow is showing, because the chlorine is 3.0, the carbon is 2.5, these electrons are going to shift toward the chlorine. So that's going to create some partial negative on the chlorines and some partial positives on the carbons. The CH bond isn't as polar, but it's similar. It's 2.5 versus 2.1, so that's going to create a little bit more partial positive on the chlorines, or on the hydrogens, I mean, because electrons are shifting away from them. So if my two chlorines are at the sites of negative, the average or central position of negative would be equidistant from both of them, right in the center. And if all my positives are here on the carbons and hydrogens, primarily on the hydrogens, the average position of positive would be equidistant to those two. And when the positive and negative end up in the same position, I don't have opposite charges on opposite ends, there's no dipole.